consider an initial value problem for a linear differential equation. Right? So we can rewrite it as y prime plus p of ty equals q of t. And recall that in order to solve it, we need the integrating factor. And the integrating factor is e to the power antiderivative of p of t dt. Well, the antiderivative is defined up to adding a constant. But adding different constants is going to give us different integrating factors. But in the end, they all are going to lead us to the same general solution of the differential equation. So if we just want to solve the differential equation, it is enough to find just one integrating factor, just any specific integrating factor. So which means that rather than writing down all possible antiderivatives, we can compute any particular antiderivative, and any particular antiderivative can be found by integrating from t0 to t. So here is the integrating factor that we are going to use. Right? So among infinitely many possible integration factors that differ by different constants, we just chose one in particular. So note that this integrating factor is, first of all, it is defined for all values of t within the given interval. Yeah, so whenever if p is defined, then mu of t is defined. And second, that it is positive. It cannot be 0 because it's the exponential function. Right? So let us multiply with this integrating factor. And then the general method tells us that then the left-hand side is the derivative of the product mu times y, which means that mu times y itself is going to be the antiderivative of the right-hand side. And the antiderivative of the right-hand side can be obtained as follows. So we take any specific antiderivative of the right-hand side and add a general constant. So that's how integration works. So the integration is always defined up to plus constant. Right? So the set of all possible antiderivatives is any specific antiderivative plus constant. Well, but then we can solve for y of t. Well, that's the general solution of the differential equation. And so this is general solution of the ODE. In order to solve the particular initial value problem, we need to find c from the initial condition. So to find c from the initial condition, we substitute. Recall that we let y be y0 and we let t be t0. So c equals mu of t0 times y0. But then recall that the mu of t0 was given by a specific formula. But then if we let t equal t0 in that formula, then we have the integral of certain point to, well, the same point, which is 0. So, and then solving for c, we find that c equals c0, y0. Well, it is important to understand that when we multiplied by the integrating factor, that since the integrating factor cannot be 0, it means that all these algebraic manipulations, they are equivalent transformations. And so when we apply this algebraic manipulation, so every next equation that we get is not just a corollary from the previous equation, but is rather an equivalent equation. So we could not have obtained more solutions by doing that. So in other words, what we have just proved is the following theorem. So suppose that we have the initial value problem for a linear differential equation. Then this initial value problem has a unique solution defined on the same interval as the right-hand side of the differential equation. Right, so the theorem tells us three things. So the first the first thing is that a solution of the initial value problem exists. So why does it? It exists because, well, we were able to find an explicit formula for this this solution. Then to say that it is unique means that there is only one solution. So there cannot be two different solutions. Why is that so? This is because whenever we did all those transformations, we always got equivalent equations, and this is due to the fact that the integrating factor is positive. So we could not have we couldn't have more than one solution because, I mean, we couldn't have lost any solution. So in the end, there is exactly one solution. And the third thing that we have is that the domain of this solution is exactly the same as the domain of the right-hand side of the original differential equation, right? So if the right-hand side of the differential equation is defined for a certain interval in t, then the solution exists and is unique on the same interval. And so here is an example. So suppose that we want to find the domain of the solution of an initial value problem for a linear differential equation. So this theorem tells us that we can do it without even solving the equation first. So first we need to rewrite it into this form where it is resolved in y prime. But then notice that the right-hand side now is undefined whenever sine t is 0. So whenever sine t is 0, then there is 0 in the denominator, so the right-hand side is undefined. So it means that the domain of any solution, it can be an interval from like minus 3 pi to minus 2 pi, minus 2 pi to minus pi, and so on. I don't know, 7 pi, 8 pi, and so on. So the domain of the domain of the right-hand side and the domain of the solution can be any interval between two neighbor multiples of pi. Well, in our case, the initial value of t is pi over 2, and since pi over 2 belongs to the interval from 0 to pi, it means that the interval where the solution is defined is exactly the interval from 0 to pi. And here is how it looks like. Okay.